we want to take the square root of them if they're a perfect square, and if not, then we're going to break it into a perfect square and another factor. So for the first example, we have the square root of 25. The square root of 25 is a perfect square. I'm just trying to think of what number I can multiply times itself to give me 25. So the answer is 5. The second example works the same way. The square root of 36 is also a perfect square, and the square root of 36 is 6. And like I said, we should have the first 15 memorized. So the square root of 196 is also a perfect square. The square root of 196 is 14, because 14 times 14 gives me 196. Okay, so an example of one where it is not a perfect square. Let's just do some examples of perfect squares. If you were here in class the day that we did these, there should be a journal entry where you made a huge list of all the perfect squares. If we have 2 times 2, that gives us 4. If we have 3 times 3, that gives us 9. 4 times 4 gives us 16. So a perfect square means we can take the square root of the number, and when we take the square root of the number, we get an integer. So if I take the square root of 4, I get 2. If I take the square root of 9, I get 3. The square root of 16 is 4. The square root of 25 is 5. The square root of 36 is 6. The square root of 49 is 7. And this list goes on and on and on. So we should have up through at least the first 15 memorized. And they were all put into your journal. And you can always Google a list of them as well. So this is what a perfect square is. So when we're simplifying radicals, okay, so before we do examples of non-perfect squares, or just irrational numbers, we have variables that can also be perfect squares. So in the first example, we have x squared. The square root of x squared is x. The reason is because I'm trying to think what number can I multiply times itself to give me x squared. Okay, the answer is x because x, as you know, may not have an exponent written here, but we do know what exponent is there. It's a 1. And when I take x and I multiply times itself, remember I add the exponents. That's from our properties of exponents from the last chapter. So x times x gives me x squared. And that's what a perfect square is. It's what number can I multiply times itself that will give me this. And the answer is x. Okay, same thing works for our second example. We have the square root of 4 times x to the third power. Anytime we have an even exponent here, and this works for numbers or for variables, anytime there's an even exponent, all we really need to do is cut the exponent in half. So the square root of 4 is 2, so I can go ahead and bring that out. And then the square root of x to the 6th power, 6 is an even integer, or I'm sorry, an even exponent. So that means that I can go ahead and just cut that number in half, and that will give me my answer, x to the third. And again, the reason for that is because x to the third times x to the third, when we add those exponents together, we get x to the 6th power. And that's going to work for any variable or number that has an even exponent. Okay, so our last example, we have a negative on the outside, and that negative is kind of just going to carry with the rest of our problem. So we're just going to bring that negative down. Okay, the square root of 64. 64 is again one of those perfect squares. So the square root of 64 is 8. And then the square root of a squared, if we take 2, we cut it in half, it is a to the 1st power, or we can just write a. And that is our final answer. Okay, so our next set of problems, just practicing more of what we had just talked about. We have the square root of 81, b to the 8th power. So again, 81 is a perfect square. So I'm going to take the square root of 81, I get 9. Then I'm going to do the square root of b to the 8th power. And again, since that's an even exponent, we just cut it in half. And that's b to the 4th power. For the next example, we have the square root of d to the 6th power times g to the 8th power. So there aren't any numbers here, but that's okay. The square root of d to the 6th, just cutting that exponent in half, will make that d to the 3rd power. And then g to the 8th power, cutting that exponent in half, will make that g to the 4th power. And after we take the square root of these numbers, we are not writing our square root symbol anymore. So our final answer is d to the 3rd, g to the 4th. Okay, and then our last example, we have the square root of x squared y to the 12th power. So again, we are taking our exponent. It's an even exponent, so we can go ahead and cut it in half. That'll be just x to the 1st, or x. And then y to the 12th power, cutting 12 in half, we get y to the 6th. Okay, so what happens if we have an odd exponent? So here we have a 3. When we have an odd exponent, what we're going to do is we're going to take our x to the 3rd, and we're going to split it up so that it has 2 bases, well, the same base. We're going to take 3, and all we do for an odd exponent is just subtract 1. Whatever's left over, that's the highest even exponent, the highest amount of even x's that we can pull from x to the 3rd. And then the extra 1 that we just took away, because when we subtract 1, that's how we got this 2. The extra 1 we took away, we're just going to add on to the end here. That's where we got that x. So all we did was we took x to the 3rd, we broke it up into x squared and x. So a few extra examples of that. If I had y to the 13th power, I'm going to split that up into y to the 12th and y. And I'll explain why we are doing that in just a second. If I have a to the 5th power, I'm going to split that up into a to the 4th and a. If I have x to the 57th power, I'm going to split that up into x to the 56th and x. The reason I'm doing that is because we cannot take the square root of an odd exponent. So x to the 3rd can be broken up so we can take the square root of the highest even amount of x's that we have, but we'll have 1 left over that'll stay under our square root symbol. So when we split this up, this will be x squared times x. We also need to simplify the square root of 50. So we're going to do that the same way we did with the other examples before we had the variables. If we take the square root of 50, I'm going to ask myself, what is the largest perfect square that can be divided into 50? And so I'm going to go through my list. I'll take 50 divided by 4, 50 divided by 9, 50 divided by 16, 50 divided by 25. I'll do that for my list of perfect squares until I find the highest perfect square that can be divided into 50. The highest perfect square that will go into 50 is 25. And then the other factor that I multiply times 25 to get 50 is 2. So when I take 50 and I divide out my perfect square, whatever the other factor is, I'm going to have to write that also. This keeps the expression equal. So I didn't change, well, I changed how I wrote it, but it's not going to change the value. 50 is the same thing as 25 times 2. So this is still the same value as this. All I did was I kind of split things up so that way I can simplify it. So now I can take the square root of 25. The square root of 25 is 5. If I try to take the square root of 2, it's going to give me some kind of very long, non-terminating, non-repeating decimal. So that means that square root of 2 is an irrational number. And I'm just going to keep that 2 under my square root symbol then. So then I move on, square root of x squared. The square root of x squared is x. And then finally, the square root of x, again, that's something that I can't take the square root of. So I'm going to leave it under my square root symbol. So my final answer will be 5x and then square root 2x. Because these were not perfect squares, and I couldn't take the square root of them. I leave them in the square root symbol. My 5 and my x came from my perfect squares here, 25. Square root of 25 is 5. Square root of x squared is x. Okay, so let's take a look at another example like that. We have a couple of variables, but it's going to work the same way. My x and my y are both going to have to be split up. So x to the third, I'm going to split that up into x squared times x. Y to the fifth, I'm going to split up into y to the fourth times y. Now, I don't have to split up z to the fourth power. The reason is because it has an even exponent. So since it has an even exponent, it is a perfect square. When I take the square root of it, I'll just get 0 squared. Not 0 squared, I'm sorry, z squared. Okay, before I do any of that, I'm going to go ahead and simplify my, my number. So I've got the square root of 48. So I try to think to myself, what is the largest perfect square that can divide into 48? So I'll take 48 divided by 4, and that actually does work out. 48 divided by 9, 48 divided by 16, and I do this until I have the largest number that I think will divide into 48. And you can keep doing this until you get to the perfect square that's larger than 48. So I could take 48 divided by 25, 48 divided by 36. The next perfect square up is 49. So anything above 48 is not, anything above 48 is not going to work anyway. So once I got to 36, I can go ahead and stop. So 48 divided by 4, like I said, that does work. That gives me 12. I don't have some kind of decimal. So this one works, but I don't know if it's the largest one, so I would keep going. Okay, 48 divided by 9 gives me a decimal. 48 divided by 16 gives me 3. So this one's larger, so far that one's in the running. 48 divided by 25 gives me a decimal. 48 divided by 36 gives me a decimal. So everything else gave me a decimal. So my largest perfect square that can divide into 48 is 16. And when I split 48 up, I'm going to split it into, no, it's too much. Okay, I'm going to split it into 16. And then the other factor that went with 16 was 3. So I split it up into 16 times 3. So again, I'm not changing my value because 16 times 3 is still equal to 48. I don't change the value of the expression, I'm just changing how I write it so I can simplify. Okay, and then I'm going to split up my x's, so x squared times x, y to the fourth times y, and then z to the fourth. We do not have to split that up because it is an even exponent. So now I take my square roots. So square root of 16 is 4. When I take the square root of it, I bring it to the outside. The square root of 3, that is going to be irrational. It's not a perfect square, so I leave it inside my square root symbol. So square root of 3. Okay, so far I've taken care of that and that. Next is the square root of x squared. The square root of x squared is x. Okay. The square root of x, again, that's irrational. I'm not going to be able to take the square root of x, so I'm going to leave it inside my square root symbol. Alright, next would be the square root of y to the fourth power. So again, taking our exponent, cutting it in half, that's y squared. Okay, taking the square root of y, that's another one I'm going to leave inside my square root symbol. And then the last one is going to be taking the square root of z to the fourth power. So I take the square root of z to the fourth power and I get z squared, and there's nothing left over from there. So my final answer is 4x y squared z squared square root of 3xy. Okay. And these last 3 practice problems are the in-class practice problems from the back of the 1.7 worksheet, 1.7D. Okay, so for the first one we have 3 square root of 48 plus 11 square root of 75. Now we've looked at simplifying the radicals, and now we are going to look at doing operations with the radicals. So before we can do an operation, at least before we can add or subtract, we need to make sure that these two square root symbols have the same number under them. So to do that, I'm going to simplify each individual term, and then I'm going to add them. So I've got 3 square root of 48. I want to simplify 3 square root of 48. So the 3 is kind of just coming along for the ride right now. We've got 3. We actually already simplified square root of 48 before, but we're going to go ahead and do it again. So the perfect squares that can go into 48. Well, 4 works. We already said that. And then the highest perfect square that works for 48 is 16, because 16 times 3 gives me 48. So I'm going to write 16 times 3. Okay, then I'm going to simplify. So square root of 16 is 4. So when I take the square root of 16 and I get 4, I bring it to the outside of my square root symbol. And then the square root of 3 here, I leave that on the inside of my square root symbol. Remember, because the square root of 3 is irrational, it is not a perfect square. And I don't want to have to do this with decimals or approximating, so I'm going to leave it inside my square root symbol. And then the last thing that I can do, now that I have 2 numbers on the outside, I can multiply those. So 3 times 4 gives me 12. And then I have my square root of 3 symbol here. Okay, now I'm just going to bring this plus sign down so that I don't forget about it. Alright, now I'm going to do this side. 11 square root of 75. Okay, so I'm trying to find the largest perfect square that can go into 75. And the largest perfect square that can go into 75 is 25. I can take 75 divided by 4, 75 divided by 9, go through my list until I get to 25. So rewriting that, I'll rewrite it as 25 times 3. Okay, then I take the square root of 25. The square root of 25 gives me 5, and I'm going to bring that to the outside now. So that'll be 11 times 5 on the outside. And then on the inside, I'll still have the square root of 3. And then finally, I can go ahead and do my multiplication. So 11 times 5 gives me 55. So I'll have 55 square root of 3. Okay, now I can add my coefficients, and then I just keep the same square root that I had. I don't add the square root symbols. All I do is I keep the same square root. So if it was square root of 3, I'll keep a square root of 3. So 12 plus 55 gives me 67. And then again, just keeping the square root of 3. We treat the square root symbols as if they are variables. So for example, if I had 3x plus 4x, if I add 3x and 4x, I get 7x. I added the coefficients, and I keep the x the same. I don't add the x's together. I do the same thing for square roots. I treat them as if they are variables. So our final answer should be 67 square root of 3. Okay, let's look at the next example. Multiplying radicals is probably the easiest operation to perform on radical symbols. So what we're going to do is we're going to take the coefficients and we're going to group those together. Next, we are going to take the square root symbols and we're grouping those together as well. So square root of 7 times the square root of 6. Okay, so 3 times 7 gives me 21. And the square root of 7 times the square root of 6 is the square root of 42. All I do is I take the two numbers, I multiply them together, and I put them under the same square root. Now, if I could simplify the square root of 42, I would, but in this case, there is no other simplification that I can do here. There are no other perfect squares that I can take out of 42. So, I'm going to leave it, and that is my answer. Okay, and then our last example, we have the square root of 8 over the square root of 24. Now if I look at these two and I realize that I can simplify that or reduce it if it were a fraction, then I am going to combine the square root symbols. So instead of the square root of 8 over the square root of 24, I'm just going to make it the square root of 8 over 24. And then I can reduce that fraction. So reducing that fraction, I get the square root of 1/3. So now that I have my numbers reduced, it's going to make my work a lot easier and simpler. So now I can go ahead and split this back up into the square root of 1 over the square root of 3. So the square root of 1 gives me 1. The square root of 3 is just square root of 3. Okay, now this is where we need to simplify one more thing before we are finished. We cannot leave a square root in the denominator. Okay, so in order to get the square root out of the denominator, I'm going to multiply that bottom number by the denominator. And whatever I do to the bottom, I'm going to have to multiply by that same number on the top in order to keep it equal. Okay, so I multiply the bottom by square root of 3, I got to multiply the top by square root of 3. And by doing that, I get 1 times square root of 3 is just the square root of 3. And on the bottom, square root of 3 times the square root of 3 is 3. And that is my final answer. I don't have anything else I can simplify, and the bottom is not a square root. And that is the end of our video for 1.7, Simplifying Radicals.